Yeah, let me unplug it at this point. Wait, how do you unplug this? Like this?
Yeah.
Okay. Computer freaked out. That's okay, no worries.
You don't say that.
Oh, no,
You never know.
it did.
Every so often I'll unplug my computer from a projector and 2 weeks later it's giving me grief about
Oh, really?
what I've been Our next talk is SpArsiTy inspired classification of malware.
Give it to the next guy. Oh, is that okay? They told me it was okay.
And I guess this is
It's my personal opinion.
Rob says in your presentation. Okay.
Good morning, everybody. I'm Lakshmanan Nataraj from the Vision Research Lab, and I present to you SATTVA, which is a SpArsiTy-inspired classification of malware variants. And this is joint work with my colleagues Karthikeyan and Professor Manjunath. So in Sanskrit, SATTVA means purity. So I'm going to explain why this method is a pure method to do malware classification. So the number of malware is increasing. In 2014, Kaspersky Lab reported that they process on average 325,000 malware per day. And the main reason for this is malware mutation, the process of creating new malware variants from existing malware. So variants are created by making small changes to the malware code or by changing the structure of the code using packers. And based on what the function is, these variants are classified into different malware families. And identifying the family of a malware plays a very important role in understanding new attacks and also blocking them. Let me give you an example here of malware variants. So what you see on the left here is our malware variants belonging to family Aluron. And on the right, we see malware variants belonging to the family Bakerian. And this representation is a visual representation, as in we map every byte of the malware to a grayscale image. And we see that these two images are similar, and those two images are similar. So there is similarity within a family, and there is also like a difference across families. And this is what we'll be exploiting in our method. So the problem statement is that consider we have a malware data set which has n labeled malware, and they're divided into L different malware families, and each family has P malware per family. So the problem now is to identify the family of an unknown malware U. And first I'll go through some related work in this field. The traditional related works are in static code analysis, which is based on disassembling the malware executable into a set of instructions, and then it usually studies the control flow of the executable, and it generates a control flow graph, which is later used to determine if a binary is malicious or not. The problem with this is that it suffers from obfuscation, or in loose terms, it's called packing. And so the next traditional method is dynamic analysis. What it does is that it takes some executable and it executes in a virtual environment, and it studies the behavioral characteristics and then draws a behavioral pattern, and based on that pattern you can say if the executable is malicious or not. This definitely does not suffer from packing, but the only problem is that it's going to take a long time for the malware to execute. It's at least like a few minutes. And some of the more recent malware nowadays are virtual machine aware, in the sense that if they detect a virtual machine, the executable is not going to do anything. It'll just be like a normal, regular file, which fools this method. And the third method is based on statistical and content-based analysis. These usually analyze statistical patterns based on the malware content, and our method is also falls under this category, and I'm going to explain more on that. The common methods are like n-grams or fuzzy hash, and also image similarity based methods. So n-grams are computed on usually the raw bytes or sometimes on instructions. It's a good statistical feature. But the problem is that n is usually greater than 1, and the bigger the n, the better the feature, and this makes it a little computationally expensive. Fuzzy hashing is a nice like midway. It generates based on the content of an executable. A fuzzy hash is generated, and similar malware have similar fuzzy hashes. But the only problem is that it doesn't work well really on packed malware. And the method on image similarity is based on my previous work, and you would have seen that on the RUM session. And the malware binaries are converted into digital images, and the image similarity features, if you're familiar with GIST features, are converted to form the malware signatures. And this is just an example of how an image similarity feature is computed. You have an image. It's resized to a small size of the thumbnail, and then it's filtered across different frequency bands. And after filtering, some statistical quantities are computed to form a large feature of the vector. The advantages are it's fast, it's compact, and it's also better than static code analysis because it works on packed and unpacked malware, and it's also comparable in performance with dynamic analysis. But some of the issues here are that how do we choose what column, which column to cut? And then in order for the method to be made fast, we have to resize the image to a small size. And if you have a very large malware, when it's resized to a small size, there's a loss of information. So to address those issues, here we take a signal-based representation of a malware. So let's X be the signal-based representation. It's similar to the image, but the only fact is that we don't consider it as a grayscale image anymore. We're just going to consider it as a one-dimensional vector. And similar as we saw before, every entry of X is just the byte value. So it's just a one-dimensional vector with the range 0 and 255. And this is how the variants look when we see it as a signal. So these are variants of the recently exposed Regin malware. You might have seen it on the news. And the fact is that they differ only in 7 bytes, both these two variants, out of 13,000 bytes. That's like you can see such a small difference, 0.05%. So what we do next is that since the malware in a data set are usually going to be of different sizes, we zero pad all the malware to the size of the largest malware, and let's say the largest malware is of length M. And now so all the malware in the data set are going to be of length M now. And so now the whole data set can be represented as an M by N matrix. Because if you remember, there are N malware in the data set, and they're all going to be represented as size M. So we have an M by N matrix A, where every column of A represents the malware sample. I'll explain. And further, for every family, we can also define a block matrix, AK, such that this matrix AK has samples only from that particular family. So the data set, the malware data set, can now be represented as a concatenation of block matrices A, where A1 to AL are going to be the block matrices representing different families of malware. And let U be the unknown malware whose family is to be determined. So U can be represented as a sparse linear combination of all the samples in the data set. So if you have like U equals A times alpha, alpha is going to be the coefficient vector. And if U belongs to a family, say K, the assumption is that it will only have coefficients from family K, and all the other coefficients are going to be 0. So alpha is going to be a sparse coefficient vector. So diagrammatically speaking, you can see that this is the unknown malware, And this is going to be a matrix of training samples. And alpha is the sparse coefficient vector which we want to find out. And this is just an illustration again. Say the unknown malware belongs to a family U. So this is the unknown malware, and these are two samples belonging to the second family. This can be represented as a linear combination of alpha 2.1 and alpha 2.2, and the rest of the coefficients are going to be 0. So now the question is, how do we find the coefficient? This can be done using basis pursued, and the solution is given here by minimizing the L1 norm minimization. And once we determine the sparse coefficients, how do we determine the family? In order to do that, what we do is we compute the residues for every family from the coefficient vector. That's done using the function pk, which selects coefficients only from a particular family. And so what we have is, once we computed the coefficient vector, we're going to compute residues for all the families, and then choose the minimum residue. And whichever family has the minimum residue is going to be the estimate of the family. And the other issue here is that the dimensionality of malware can be high. So a malware can be 200 kilobytes, or it can also be 2 megabytes. Sometimes in our data sets we get malware which are 9 megabytes. So it is not very practical if to work in such a large range. So what we do is we project the malware to lower dimensions using random projections. So this is different from resizing, because in resizing it's going to be all just interpolation, and we're going to choose coefficients based on that. Whereas here we're just randomly projecting, and that's one difference between our previous method where we used image resizing. And let R be the random matrix, and it's going to be a D by M pseudo-random matrix, and D is chosen such that it's much lesser than M. Typical values will be like 500 or 250 and things like that when compared to like 9 million. And I'll discuss that more when you come to the experiment sections. And once we project it to the lower dimensions, the sparse solutions can still be obtained because the alpha is going to remain the same, and W and only the RA, and we need to find the same solutions to the whole. So the complete approach is given here. So we have the malware data, and we represent the malware as a signal, and then we do a sparse kind of modeling. And since sparse kind of modeling doesn't hold well for large malware, we project it to lower dimensions, and the same sparse model holds well in lower dimensions as well. And now the question is, I initially talked about malware variants, so how do we model them? If you remember, the malware variants are created by making small changes to the code. So there's a good chance that they share commonalities between both codes. So we model a new variant as U dash, as U is the original malware, and U dash is the variant, and EU is going to be the error vector. And this equation can be represented again in terms of block matrices, as where U dash is can be a concatenation of A, which is the malware data set, and IM is now an identity matrix, and we have alpha and EU as the column, and this is again another system of equations, but this system of equations, if you see, will always be underdetermined because of the fact that we have A and IM, and sparse solutions can always be obtained. This matrix is a fat matrix, and it's always going to be underdetermined. And the similar solutions, the same thing, what we did before, projecting the system of equations to the lower dimensions, it can again be done here. And the same way as we found the residues, we find them again lower dimensions, and we use this set of equations to determine the family of the malware. So no more maths. Now I come to the experiment sections. So we use two data sets for our preliminary experiments to see, first find a proof of concept. One is the mal-image dataset, and the other one is malware dataset. The first dataset has 25 families and 80 samples per family, where the second one has 23 and 20 samples. And you can see the value of M is really large. As I mentioned before, it's 840,000 for the first case, and it's 3 million for the second case. And we project such a large matrix to just dimensions between 48 to 512. We did try more than 512, and there wasn't a huge difference in terms of accuracy, so we stopped at 512. And when we go below 48, the accuracy drops really bad. So these are the dimensions we use. And we compare the method with gist features, what I previously explained. And for classification, we use two different classification methods. One is the SpArsiTy-based classification, which I explained in the previous slide. And the other one is the nearest neighbor, which was used previously for gist features. And we use 80% for both data sets. We use 80% for training and 20% for testing. So first, I'll show the results on the mal-image data set. We see that the red curve, that the combination of random projections and sparse representation based classification outperforms the other two. The best accuracy of 92.83% was obtained for this combination at a dimension of 512, and you can see that below a dimension of 48, all the features perform poorly, and beyond 512 there wasn't much difference in terms of performance. And the gist features had almost the same accuracies in the ranges of 88 to 90%. However, the lowest accuracy was for the combination of random projections and nearest neighbor. So this means that for this data set, the projections in lower dimensions were not really closely packed, but the SpArsiTy-based representation were still able to obtain a good classification accuracy. And for the malware data set, again, the combination of random projections and sparse representation-based classification had the best performance. And similar to the previous case, the gist features were almost, for both classifiers, were almost the same, around 93%. However, the combination of random projections and nearest neighbor had an accuracy of 96%. So this kind of shows that for this data set, the projections in lower dimensions are more closely packed. So so a nearest neighbor based classifier also works well in this case. And now what we do is we compare our method with other static analysis features, statistical analysis features. I mentioned about the fuzzy hash based technique. SSDeep, I don't know if you're familiar with SSDeep, is a common way to hash a malware and to find similar malware. And we also use n-grams, and we use n equals 2. So the dimension of this feature is 2 power 16, which is like 64,000, which is really large. And we see that for both data sets, the combination of random projections and SpArsiTy-based classifications outperform all the other methods. So one issue with malware classification is that the malware labels are not really well defined. This is because an antivirus software, one antivirus software gives one label for a malware. Another antivirus software will give another label. And most of the times, these labels do not agree with each other. Sometimes one antivirus software may say a sample is benign, whereas another one is say suspicious. So what normally in academic research, what people do is they either take one specific antivirus software and try to prune the labels for that, or they take a bunch of software and try to just find the common labels between them and use only those common labels. We're going to see how this approach can help in like you can say if there are no how I put it is that in some cases there are like singletons which antivirus softwares do not agree with each other, and this approach can actually find those singletons, and I'm going to show you how. So we call those samples as low confidence samples, and these are samples which the antivirus software may not agree with each other. And this can be found using a SpArsiTy coefficient index from the coefficient vector we obtained earlier. And a value of 1, this is like more like a confidence measure. The value of 1 says that the test sample is going to be a linear combination from only one family, which is really a good measure. But if it is 0, then this test sample is spread across all families, and this is probably not a very good label. And we can give them low confidence or also reject them if saying that this is not a good label. So for both data sets, what we do is we fix D as 512 and vary the threshold for the SpArsiTy coefficient index. And we see that an accuracy is more like a precision here, and a precision of 100% is achieved when the threshold is 0.5 for the first case. At this step, like 25% of samples are rejected, and a precision of 100% is achieved for the second data set when the threshold is 0.6, at which only 5% samples are rejected. The more details about this experiment are there in the paper, so I'll just briefly say. So we can see that the threshold is varied from 0 to 1, and at 0.5, we can see that the accuracy is, at 0.6, the accuracy reaches 100%, at which 5% of the samples are rejected. And the last part is that the way to compute the sparse coefficients is usually done using basis pursuit. Sometimes this gets very computationally expensive. So there's another method called orthogonal matching pursuit, which is a greedy method to do L1 norm minimization. OMP is several times faster than basis pursuit. It's like for 18 times in the case of MalImage and 30 times for the second data set. But the problem is that since this is a greedy and approximate L1 norm minimization, the accuracy hits a little bit, drops a little bit down. So for the first case, the accuracy was 89%. For the second case, however, it's not that bad. It's still 97%. But the timing is at least 24 times, it's 18 times for the MalImage data set and 30 times for the Malware data set. So for large-scale experiments, we're going to use orthogonal matching pursuit in order to compute the coefficient vectors. So for our large-scale experiments, we use two large-scale diverse data sets, and there's no reported results on any other paper on this data set. Because one of the data sets is our own data set, and the second one is public, but nobody has really reported any results on that. So we used orthogonal matching pursuit on both with 80% training and 20% testing. And the first data set, you can see, this is actually a public data set. It's offensive computing. If you just type it, you can download such a large data set. It has 2,124 families, or like 2,000 classes. So we're going to do a classification with such a large number of classes. And it has 20 samples per family. And you can see the value of N and M is really large. And this is a data set which has many families and fewer samples per family. And the second data set is the Anubis data set, which is from the, if you're familiar with the Anubis dynamic analysis platform, we got it from there. And it has 209 behavioral cluster labels, and it has 176 samples per cluster. So this data set is different because from the other one because it has fewer classes, but more samples per class. So we're going to see how our method performs for these two diverse data sets. So on the first data set, we for 2,124 families, we got an average accuracy of 66%. That's, I think, pretty impressive. And we see that 927 families had an accuracy of 100%. And for all these 927 families, the value of SCI was 0.97. And this shows that the SCI, which we designed it as a confidence measure, is really a good confidence measure. And at a threshold of 0.6, we see that the accuracy drops to like 77%. When 24% of the samples are like rejected because they could be like low confidence samples. And the overall computation time for this experiment on a standard machine was 4 hours, and this was just done using MATLAB. So definitely better if you use better methods, the time can be reduced further. And on the Anubis data set, the classification accuracy was 57%, although there were only 209 classes. And 27 classes plus clusters had an accuracy of 100%, and 50 had more than 90%. And the SAI value was 0.97 for this too. And at 0.6, the accuracy was 77%, with 34% of samples rejected, and the computation time was 3 hours in this case. And we see that for both these data sets, the accuracy at an SAI threshold was of 0.6. And if you remember, this 0.6 was obtained from our preliminary experiments, was 77%. And we also see that the computation time depends both on the number of samples and the number of classes. So our future work is going to be, in this work, we had projected one full malware to lower dimensions. However, an executable consists of many sections, and it would make more sense to divide an executable into different sections and then randomly project them to lower dimensions. So that now a malware can be, you could represent the malware as a bag of randomly projected features and use that bag as a signature rather than using just one single signature. And that's one. And the second part of the work is that I mentioned about how the variants are modeled. In this work, we only try to estimate the family, but from the way we model the variants, we can also see where exactly a malware is changing, because that's how we modeled it as. So in my next work, I'll be working on how, given a large number of variants, I'll be using this method. I'll be finding out where exactly these variants are changing and how they evolve. And in conclusion, we presented a method for identifying malware families using a combination of sparse representation-based classification and random detections. And we represent malware as signals, and I think this will open up the avenues for using other signal processing techniques to analyze malware. And we also showed the scalability and efficacy on really large data sets. And thank you for the talk. Thank you for listening.
Time for a couple of questions.
Yes.
A couple of questions. So, if you throw non-malware, so benign application at this,
Yes.
presumably your confidence intervals, what filters that in?
Yeah.
Okay. And then, do you have results specifically for binaries that are packed?
Yes.
And
Yes.
what are your accuracy rates for those?
So pack, it depends on the packer, first case. But for simple packers, by simple packers I mean like UPX, ASPack, FSG. The accuracies are very high. But if you use a complex packer like, let's say, Temida or TE-Lock, they're going to use a lot of encryption, and the accuracies there drop.
Okay.
So that's what my research showed.
Okay, so it's dependent on the packing algorithm.
Because UPX, for example, uses a weak encryption, and you can still see the differences even after it's the similarity even after it's packed. So UPX is very easily detectable.
So that when you talk about the differences, you're talking about those vectors of variance that you built with the differences.
Yeah.
So how do you build those initially?
How do I build what initially?
You had mentioned that the binaries that or malware that had variants associated, where you had multiple variants, you were able to build a vector of that based on the difference in those variants, like where they change. I think is what you were saying, right?
That's how we model it as.
That's right, yeah.
Yeah. Right now we have two variants, and we are just considering both these variants as signals.
Mm-hmm.
But we modeled these two variants using the error model. But for this, we only use it to estimate the family. But my future work is going to be on where exactly, like using the error to find out where exactly the malware is changing.
So how does it build that error? So that's more so my question.
How is the error estimated?
Yeah, if you don't know that they're from the same family, how do you build that initial model?
Oh, okay. So the assumption here is that we have the malware data set has families. We have like if there's a family and it has variants which are similar.
Oh, it's already been done. Okay.
Yeah.
Okay.
So that part is already been done. If it's not done, then the confidence threshold will give it to low confidence,
Right,
and
exactly.
it will throw it away. So the sparse coefficient vector is what tries. That's the part which estimates that.
Okay, so the assumption is you have a lot of the variants already in your database.
Yeah,
Okay,
that
gotcha.
is it's a more like a database-driven approach. Yeah.
Hmm. Thanks.
Thank you.
And our last presentation for the session is thumbnail preserving encryption for JPEG.